Thanks for tuning into the Division Zone Maths video. In this video, we're going to be solving modulus inequalities. So this follows on very nicely from actually solving modulus equations. And indeed, our approach to sort of solving modulus inequalities will be to convert them to modulus equations and to graph them, and then to work out the points of intersections of the various graphs, and then sort of look at the overall thing graphically on the coordinate system and be able to just say on what chunks is the inequality going to be satisfied, right? This is very much like the sort of thing one would do when we look at quadratic inequalities in particular. So let's actually jump in. So we want to solve this sort of first example where we've got the modulus of 5x minus 1, and we want that to sort of be always bigger than 4. And of course, that's not always going to be true, but we want to find all the values of x for which it is going to be true. So a good place to start would be just to get a sketch of modulus of 5x minus 1. So let's take a look at that. So we start by sort of just sketching 5x minus 1, the graph. So we know it's going to be a straight line. It's going to cross through minus 1. And you can sort of think about this, it's going to cross through a fifth on the x-axis. But obviously, this is the graph of 5x minus 1. We want the graph of the modulus of 5x minus 1. And we saw a lot of this in the sort of previous videos in this series, which is when you take the modulus of something, you just reflect only the things that are actually below the x-axis to sort of being above the x-axis, and the things that are already above the x-axis, you leave them alone, right? So that's what we're going to do here. So we end up with this. So now this green graph is the graph of our modulus function, but of course we want to know what these branches are, because the branches are just things in their own right which don't have modulus signs, okay? So of course I want the algebraic description for the modulus of 5x minus 1, and we use the definition of the modulus function. We say, well, if the thing on the inside is positive, we leave it alone. And if the thing on the inside happens to be negative, we basically just put a negative in front of it, okay? But of course, we can sort of tidy this up a bit further. So in particular, we can expand that negative on the inside and get that. And then obviously these inequalities of domains, we can actually sort of simplify just by rearranging directly. So we actually end up with this. So now looking at the graphs, I know that this thing here has a positive gradient, so it has to be described by this, and it's reassuring that it's actually defined for x bigger than or equal to a fifth, which is obviously this chunk here. And then this thing here has a negative gradient, so it has to be described by this. And again, that's defined entirely for x being less than a fifth, so it's actually going to be all that chunk here. So that's consistent. So now we want to put the graph of y equals 4 on there, so let's do that. So we end up with a graph of y equals 4. And of course, what we want to do is we want to work out what these intersections are. And then when we know what those intersection x values are in particular, we know that for everything else on the right, because the green graph is above the red graph, then the inequality is going to be satisfied. And the same thing is going to happen for everything on the left, because the green graph is again above the red graph, then for all those sort of x values, the inequality is going to be satisfied. So let's basically solve things simultaneously to work out the solution for that point. Well, we know that it's going to be this branch and y equals 4. So I'm just going to say I want to solve 5x minus 1, and I want that to be equal to 4. And that basically tells me that 5x has to be 5, and that tells me that actually x has to be 1. So we've been able to basically work out what this x value here is. It's 1. We repeat the same thing for the second intersection point, but of course now we've got the other branch of our modulus function now crossing the line y equals 4. So we solve another equation which is going to be minus 5x plus 1. That's the left branch of the modulus function equals to 4, which actually gives us minus 5x is actually equals to 3, because I take away 1 on both sides, and then that tells us that x actually has to be minus 3/5, right? So we've basically also worked out this x-intersection here, minus 3/5. So we know what the solutions are going to be. The solutions are going to be this entire x interval here and this entire x interval here. And because we have a strict inequality, we don't actually count those x values by themselves, okay? So I can just write down the solution. I can say solution is x has to be less than 3/5, or x actually has to be bigger than 1. So we've been able to solve the very first question. Let's take a look at example 2. So in example 2, we have very much the sort of thing we did in the previous example. In fact, the modulus function we have is exactly the same as the one we had in the previous example, but now we've actually got a double inequality of sorts rather than just one. As always, there are multiple ways forward here, but I'm going to be consistent with respect to the approach we used in example 1 and actually use sort of the graphical approach in this example as well. So let me just talk you through what we have here. Obviously, the green graph is the graph of our modulus function, and then this graph here is basically the line y equals 11, and then this graph here is the line y equals 5, obviously. And given what the inequality actually asks us to find values of x for, which is all the x values for which the modulus function lies between 5 and 11, we can just see from here it's going to be this region here, and it's going to be that region there of our modulus function. And of course, that would then have corresponding x values. So we're actually going to have two separate intervals of solutions for which our modulus function is going to satisfy these inequalities, and to be able to work out those intervals, we need to work out the x values at each of these points. So we're going to sort of do them systematically. Let me do it in red actually. So let's start with the top one here. So to be able to get that point there, I need to solve this branch with y equals 11. So I'm just going to say it's going to be 5x minus 1 equals 11. And then that tells me that 5x is actually equals to 12. And that tells me x is actually equals to 12 over 5, which is, I believe, 2.4. Okay, so if I come down here, if I can actually do a decent job of this, I would end up somewhere here, which is obviously going to be something like 2.4. I've now got to go away and work out that x value there. So let's see how we're going to solve that. Obviously, we're going to have this negative branch here, which, given that this is the exact same modulus function as last time, it's going to have the exact same description as we had in the previous example. So we know that the negative branch is given by minus 5x plus 1. So let me write that down. And we know we're still solving this branch against the line y equals 11. So let me write that down. So now when I take away 1 from both sides, I get negative 5x is actually equals to 10, which tells me that x is actually equals to 10 divided by negative 5, which is obviously negative 2. So if I come down from here, if I don't lose track of my pen, I actually end up at negative 2 perfectly. Okay, so we've worked out 2 points. Let me go away and work out the other 2 points. So let's focus on this one here. And again, so the branch is 5x minus 1, but the y value now is 5. So I'm going to solve those simultaneously. So it's going to be 5x minus 1 equals 5, which actually tells me 5x has to be 6, which actually tells me x has to be 6 over 5, which I believe is 1.2. So we've worked this out. This thing here is 1.2. And then we need to go away and work this point here out. And it's the exact same process, which is this branch here, which is minus 5x plus 1, and the line y equals 5. So it's going to be minus 5x plus 1 equals 5, which tells me that minus 5x is actually equals to 4, which then tells me x actually is minus 4/5, which is minus 0.8. Okay, so we end up with minus 0.8 there. And so we've basically done all the hard work. Now it's just really a matter of making sure that we understand that those inequalities are strict and they're not sort of soft inequalities. And therefore, the solution that we're actually going to end up with are going to be this sort of region here and this sort of region here, because it's precisely for x being between these values that we actually have the green part of our modulus function is actually between these two horizontal lines. And the same is true for this chunk here, that the green part is actually in between these two horizontal lines. So I can just now say, so my solution is actually x has to be between negative 2 and negative 0.8, or x has to be between 1.2 and 2.4. Okay, so let's have a look at the next example. Example 3, we have very much the sort of thing we've already been doing in the previous two examples, but now we actually have a linear function as opposed to just a constant. So let's try and work this out. So we have the exact same modulus function. So because we want to solve this graphically, we go and plot our modulus function. We should be very comfortable with being able to do this. And of course, we can also expand out the modulus function sort of algebraically. So this is here the algebraic description of the modulus function, and we can see that it has two branches, and these are the respective branches. This one's the first branch, which has a positive gradient, and this one's the second branch, which obviously has a negative gradient, right? So the other graph is the graph of y equals 3x, and we see that we want the modulus function to be bigger than 3x, which means we're interested in this sort of region here, where the green graph is actually on top of the orange graph, right? So we need to figure out what these points here are, which we're going to do by solving things simultaneously. So let's solve for that sort of point there. So we know that it's going to be this branch here with 3x. So let's do that. So it's going to be 5x minus 1 equals 3x. And of course, I rearrange this to take 3x to the left-hand side. So 5 minus 3 is going to give me 2, and the x is just there. So I have this, which of course is nothing other than saying 2x is 1, and that's nothing other than saying x is actually equal to a half. So we've been able to figure out that this value here, if I hold my pen carefully, is actually going to come and meet at a half. So that's pretty reassuring. We need to work out the second point here, right? So again, here we're going to do the exact same thing, but now we're going to have y equals 3x intersecting with the second branch, right? Which is minus 5 plus 1. So I'm going to say minus 5x plus 1 is equals to 3x, and that basically tells me that if I take the 5x to the other side, I'm going to get 3x plus 5x, which of course is just 8x, and so my x actually happens to be 1/8, right? So if I come here, this thing here is going to be 1/8, and that's reassuring because I've actually got a positive solution, so that's consistent with my graph, right? So we want, as I said, this chunk here and that chunk there. So if I actually go and sort of mark this out, I'm going to have this region, and I'm also going to have this region. And of course, because the inequalities are hard, then these points are not actually included. They are excluded, right? So I can now write down my solution. My solution is x actually has to be less than 1/8, or x actually has to be bigger than a half. So this was straightforward. Let's try the next example. So this example takes us closer to the sort of thing we're going to see on an A-level paper actually. So in this case we have an inequality, it's a modulus inequality, but the interesting thing is we've got a modulus function on both sides. Okay, so given the importance of this sort of a calculation, we're actually going to do this two different ways just to really reinforce these ideas. So our approach one is going to be the same sort of way that we've been doing these questions so far, which is we're going to graph it, we're going to then set things equal to one another, solve them simultaneously, work out solutions, and then use the graphs to be able to write down the answers. Okay, so I'm not going to dwell too much on how to graph these things. If you're uncomfortable with that sort of stuff, please go back and take a look at previous videos. What I am going to do is actually apply the definition of the modulus function and actually expand this out to get an algebraic description in branches. And that's because we're going to need to know what the branches are to be able to equate them to other branches and to be able to solve them simultaneously, right? So let's now expand this thing here algebraically. We actually get this. So the significant step is probably from here to here, which is nothing other than saying something like if you've got, say, minus x, and if you take the modulus of that, that's the exact same thing as the modulus of x, where x is any number you can think of. Of course, we proved this property a few videos ago, so if you're not sure about this, go back and take a look. So perhaps I should write down what I mean. I mean this. So it's going to be 3 minus x is equal to modulus of minus 3 plus x, which is obviously the same thing as the modulus of minus x minus 3, which now using the sort of property in red here, it's just the same thing as x minus 3. Okay, so that's the first step. And then from that point onwards, life is very easy because we've just literally applied the definition of the modulus function to be able to write these things down. And then these are just simplifications of these things here. So let's now graph these things. So we end up with something like that. We see that this graph here is actually the graph of 2x minus 1 modulus of, and then the red graph is the graph of 3 minus x modulus of, okay? And we see that there are indeed going to be two intersections, and we want to solve this inequality, which is the same thing as saying the black graph is always higher than the red graph, okay? And we see that's the case on that chunk there, and on that chunk there. So we solve for these points. So let's do that systematically. Let me go to a different color. So how do I work out what that point there is? Well, I need to know what this branch here is, okay? And I can come to this description and I know this branch has a positive gradient, so it actually has to be here. And indeed, x has to be bigger than a half, and that point there is actually past a half. So this branch here is basically going to be 2x minus 1. And I want to solve it with this branch here, which actually has a negative gradient, so it actually has to be this thing here, right? So I know that this branch here is basically minus x plus 3. So I solve these two simultaneously. I actually say 2x minus 1 is equal to minus x plus 3, which tells me that 3x is actually equals to 4, which tells me that x is actually 4/3. Okay, so that's one solution. So we know that this point here is basically 4/3. And that makes sense because 4/3 is less than 2 and it's more than a half. And then we come back and we try and solve sort of for the other point. Let's mark that in a different color. So that point there, and of course now I'm going to have this black branch with this red branch. So this black branch is obviously going to have a negative gradient, so it's got to be this one here. So let me just say that. So this is going to be minus 2x plus 1. So when I now go to solve this, I'm just going to say it's going to be minus 2x plus 1 equal to this red branch, which is obviously given by that. So it's going to be minus x plus 3, which we can then rearrange. If I take the minus 2 to the other side, I actually end up with 2x, and then I have this, which I further rearrange. I take the 3 to the other side, and I simplify the right-hand side. So indeed, we've worked out x to be minus 2. So let's mark that on here. And in fact, if I hold my hand carefully, then there you go. This lines up perfectly, and therefore we know what the solution is. This thing here and everything on the right hand side, and this thing here and everything to the left hand side. The important thing is the inequality is now soft, which means actually the actual value at 4/3 gets counted in, and also the actual value at minus 2 gets counted in. So that's quite important. So let's now just write that down. So our solution is actually x is less than equals to minus 2, or x is bigger than equals to 4/3. So that's easy enough. Let's take a look at the same exact problem using method 2. So we've got 2x minus 1, the modulus of, and we want to solve it such that it's always bigger than 3 minus x, the modulus of, right? I'm going to use a property, which is if I square both sides, I can actually drop the modulus sign. Okay, this was proven in one of the previous videos, so I can do that, and then I can basically do that. And that makes life now so much easier because I've managed to basically convert something which was a modulus inequality to something which is just an inequality about quadratics, okay? So let's now expand this out. So when I expand this out, I'm going to get 4x squared minus 4x plus 1. And then the right-hand side is going to give me 9 minus 6x plus x squared. And then I can sort of collect terms. So I can say 4x squared minus x squared minus 4x plus 6x plus 1 minus 9 is bigger than or equal to 0. And of course, this is nothing other than saying 3x squared plus 2x at minus 8 is bigger than or equal to 0. And at this stage, we've got to basically go to a graph, right? That's the way we were doing these in the first year at A-level, more often than not. Then let me just for now factorize this. So it's going to be something like this because 3 is obviously prime, so nothing else is going to go with 3. And then that can be split up into a 4 and a 2. So now we need to have an idea of what the solution is actually going to look like. So let's quickly draw a graph for fun. So we're going to have the intersections are going to be at minus 2, so that's there. And it's actually going to be at 4/3, so that's going to be maybe about there, right? And of course, it's a happy quadratic, so it's going to look overall, it's going to look something like that. And then it's going to do something like that, right? And now the same problem has basically come down to me solving this quadratic being bigger than 0 or bigger than equal to 0. So I see actually all that chunk there and all that chunk there. And of course, I have to include that point there, and I've got to include that point there because of the soft part here. Okay, so we've basically got a solution. So we know that the solution is actually x being less than equals to -2 or x being bigger than equals to 4/3. Okay, so I hope you found that useful, just seeing how there are multiple ways of sort of doing the same question. And perhaps you might even think that this method is actually much easier, but in fact this method sometimes makes life a bit harder, and perhaps we can take a look at some cases where that happens to be true. But for now, let's move on to the next question. Example 5 is another standard sort of a modulus inequality. Let's jump straight in and figure out all the x values for which this inequality is valid. And we're going to basically apply approach 1, right? So if I now do that, which is we want to be able to expand this out using the definition of the modulus function, and we want to be able to expand that out using the definition of the modulus function. And in fact, I've just done that here. And this is the simplified version for this function here. And that's the simplified version for this function here. And these are sort of fairly straightforward things. You should be comfortable with this. Let's now take a look at the graphs. And of course, this is the graph of 2 times by the modulus of x minus 4. And then the black graph here is the graph of modulus of x minus 1. And indeed, we could just go plot these and sort of see that for ourselves, and the same would apply for that. But actually, there are much easier ways of being able to see the graphs of this and this, right? So for example, the graph of that thing here, which is this thing here, is basically the same as the graph of modulus of x, but shifted one to the right, okay? And we sort of see that. It's literally modulus of x just shifted one to the right. So that point there is x equals 1. And likewise, the graph of x minus 4 modulus is actually the same as the graph of modulus of x, but now shifted 4 to the right. Okay, we see that again. So we see that point there is x equals 4, and then of course the red graph is basically a stretch of the green graph by scale factor 2. So that height there has been doubled to give you this height here. And the same would hold true for say here. So this height here has been doubled to give you this height there, right? So anyway, so these graphs are nice and lovely, and the ones that we're actually interested in, as I say, is the red one and the black one. So we want to be able to solve these branches in some way. So let's figure out what that point there is, right? So we know it's going to be the right branch of the red one, and it's going to be the right branch of the black one. So the right branch of the red one is this one here with a positive gradient. So it's going to be 2x minus 1 or 2x minus 8 even. And that's going to be equal to this black branch here, which is just x minus 1. And we solve this, so we say that's the same thing as saying x is actually equal to 8 minus 1, which is actually 7. So we know that this point here, actually when we come down, it's going to be x equals 7. And now we want to go away and solve for that point there. So we want sort of this branch here, which is the second branch of this modulus function, which is obviously with a negative gradient. So it's got to be this one here. So it's going to be minus 2x plus 8. And it's going to be equal to the same branch of our earlier modulus function, right? So it's still going to be sort of x minus 1. So let's do that. So x minus 1. And then we can sort of solve this. If I take the negative 2x to the right-hand side, I end up with x plus 2x. And then obviously we have that. If I take that negative 1 to the left-hand side, I end up with 8 plus 1, which is 9. And then the x plus 2x on the right-hand side gives me 3x, which of course we can solve to say x equals 3, right? So if I come down here, I can see that actually 3 fits perfectly between 2 and 4. So that's quite reassuring. Now that we actually have our x values, we are interested in the regions where x minus 1 modulus is bigger than 2 of x minus 4 modulus, right? So in other words, we want the cases where this black graph here is higher than that red graph, okay? And that's clearly true only between 3 and 7. So let's explicitly mark that. So it's going to be between 3 and between 7. And because that inequality is a hard inequality, then the 3 and 7 are not actually included. So we have this. So I can basically now say our solution is x is actually bigger than 3, but it's strictly less than 7. Okay? So that completes this question. Let's take a look at the next example. Example 6, this is very much like example 5, but now the modulus function we have actually on the right-hand side is a little bit more involved. And of course, to sort of make life a bit easy and also in the interest of time, I've actually got a lot of sort of stuff already laid out. So let's go through this systematically to try and answer this question. Right, so our approach is, as always, we want the graph of that and we want the graph of that, and then we would know which branches are intersecting, and then we would be able to sort of work out the points of intersection and then use the graphs overall to be able to work out the answers, right? So 2x minus 1 modulus is actually nothing other than this thing here, and you should be sort of okay in being able to get that graph. And then the other one is 4 minus the modulus of x minus 1. Well, okay, that might be a bit more work to figure out, but we can do it quite easily because we can just start with the modulus of x, and then we can shift that one to the right to get modulus of x minus 1. Right, so we start with the modulus of x, then shift it one to the right to get this black graph here, which is modulus of x minus 1. And then we reflect the modulus of x minus 1 about the x-axis to get minus the modulus of x minus 1, which is this green graph here. And then finally, to be able to get 4 minus the modulus of x minus 1, we just take minus modulus of x minus 1 and just add 4 to it. And that's the same thing as a transformational shift of 4 sort of vertically upwards. So we go from that green graph to that red graph. So that red graph is actually the thing we're interested in. And of course, the other graph was the orange graph was the thing that we were interested in. So we know that these are our 2 points that we want to solve for. And to be able to do that, we of course will need to turn to these branches. So unsurprisingly, I've managed to get these just by applying the literal definition of what the modulus function is here and also here. You could perhaps work through that yourself to make sure that I've not made a mistake here. So let's now actually figure out what this point of intersection there is, say, right? So I know what's happening here. It's this branch here, which is 2x minus 1, and it's this red branch here, which indeed is just minus x plus 5. So let's write those down. So it's going to be 2x minus 1, and it's going to be minus x plus 5. And then we just sort of solve this, and we basically get the minus x goes to the left to give us 3x, and the minus 1 comes to the right to give us plus 1, so it gives us 6. So x actually happens to be 2. So if I come down here, that makes good sense because it's lining up with 2. Let's now look at the other thing here. So we know that we have this branch, which is minus 2x plus 1. And then we have this red branch, which is just x plus 3. So let's put those equal to one another. So we have minus 2x plus 1, and then we have x plus 3. And again, we solve these. So in this case, I'm going to take minus 2x to the right to actually give me 3x on the right. And I'm actually going to take the 3 to the left to give me minus 3 on the left. But 1 minus 3 is obviously going to give me minus 2. So I actually end up with this. And we can go on and solve this and say that's just minus 2/3. So if I now come down here, this is minus 2/3. So now that we have our solutions for the x values of those coordinates, let's now think about our inequality. What we actually want is we want the modulus of 2x minus 1 to be bigger than this thing here, right? But the modulus of 2x minus 1 is this orange graph, and we want the orange graph basically to be higher than that red graph, okay? And we see actually that for this entire region here, the orange graph is indeed higher, and also this entire region here, the orange graph is respectively higher compared to the red, right? So we can just sort of mark those regions. So we come here and all of that region works for us, and we also come here and all of that region works for us. And because the inequality is a strict inequality, I don't count that point there and I don't count that point there. So we can actually write the solution down. So our solution is actually going to be x has to be less than negative 2/3, or x actually has to be bigger than 2. Okay, so we've managed to figure this out. Now, I should actually say a couple of things here. The first thing is as follows. So if we actually consider a vertical line, and if we actually slide that line from the left to the right, we actually see that for the entire blue region, that I've marked, actually the orange graph is higher than that red graph when you compare it with respect to this line, okay? And that's the key idea. So that's the case here, and also that's the case here. So we see that the orange graph is actually higher than the red graph, right? Now, the fact that the red graph is higher than the orange graph in the middle, that's completely okay. And this is precisely the interval in which the inequality for this question is not satisfied. But the one thing you might worry about is as follows. You might think to yourself, well, hang on, that point there is higher than this orange point here, right? The point is you need not worry about that point there compared to these orange points here, because really you only want to be comparing them for each input of x, right? Which means the comparison that sort of makes sense is really along a vertical line, okay? Not along some horizontal line. So that's the first point. I hope that's clear. The second point actually is, if I actually make a bit more room, it is not easy to actually solve this inequality using approach 2 that we've seen in previous questions. Okay, so in other words, if I went to this and said, well, let me just square both sides, and the idea is when I square both sides, I can use a property that I can just drop the modulus sign. Well, if you do that, it's not really going to work here, right? And this is why, because when you actually square both sides, so the left-hand side is fine, you can just drop the modulus sign directly, but when you square the right-hand side, you're actually going to get cross terms coming out, right? So of course the 4 squared is going to give me the 16, so that's completely okay, and the x minus 1 modulus is going to be squared to give me x minus 1 modulus squared, right? But that's just going to be this thing here, but the cross term is going to be 2 times by 4 times by negative of modulus of x minus 1, which is negative 8 modulus x minus 1. So the point is, even though we've squared both sides here, you've still got a modulus on this side here, right? So there are ways to go on and still get rid of that modulus and still apply method 2, but usually it's a lot more work. So I would recommend just using approach 1 where possible, but it's good to know that there are certain cases where approach 2 would take a lot more work. And just to be sort of careful about that. Right, so let's try the next example. Example 7 is a lovely example. It uses slightly different sort of language, but really we're doing the same thing. So we've got some sort of modulus function. Here we're taking the modulus of a quadratic. And then we've got a linear function, and the question wants us to figure out all the x values for which the f of x function is going to be bigger than the g of x function, okay? So let's see what the solution is going to look like. So we want to try and actually get the graph of this f of x function, and how are we going to do that? Well, we're going to plot this quadratic, and then we're going to reflect the bottom half of the quadratic sort of in the top half, okay? That's a standard way of being able to get a modulus of a function. So to be able to graph this quadratic, it's worth factorizing it. So I know that the x-intercept is going to be at -8 and the other one's going to be at -1. So let's see what this looks like. So here we have it. So that point there is -8 and this point here is -1. And we see that actually this sort of orange graph is already the graph of f of x, because this would have been the bottom part of our quadratic, of our parabola, but now it's been sort of put up into the top half of our plane. So that's our sort of f of x, and then g of x is our straight line. So we now want to figure out all the points where they intersect. So the intersection is going to be here, there, there, and there. And indeed, we then want to go on further and actually figure out all the x values for which the f of x is going to be sort of bigger than the g of x. In other words, the f of x is going to be higher. So that's for that region there, that's for this region here, and that's also for this region here. So we certainly need to know these x values, so we can now go figure these out. So let's try to figure out sort of this x value here. Let's call it 1. So how are we going to do that? Well, it's going to be an intersection between this part of our quadratic and the line sort of 1 minus x. But I want to be able to write down what this looks like, so let me actually do it here. So perhaps what I'll do is I'll say f of x is modulus of x squared plus 9x plus 8. So the two branches are actually going to be, there's going to be sort of a top branch, which is just going to be the function, and then there's going to be the bottom branch, which is actually going to be negative of the function. I'll not worry about writing down the actual domain, because that would just make life a little bit harder, but it's pretty clear what domain these things are working for. So for first point, we're going to have the 1 minus x, intersecting with the regular positive part, okay, of our initial quadratic, which is going to be that. And then we can sort of solve this because we can just say this is going to give us x squared plus 10x plus 7 equals 0. And this, of course, needs completing the square. So I'm just going to say half the coefficient, square the whole thing, take away the thing that I've actually got, and then add 7. And that's, of course, the same thing as x plus 5 all squared minus 25 plus 7 equals 0, which tells me that x plus 5 all squared is actually the same thing as 25 take away 7. And so we can go on and take the square root and basically figure out the solution, right? So that's what we have. Now, we've actually got two solutions, okay? So we need to be very careful about which solution it is that we've actually figured out for this particular point and what the other solution may or may not mean, okay? So in fact, if we come back to our sort of function and think more carefully about what's happening, one of the reasons why I was hesitant to write down the domain actually was because of this observation here, right? So think about this. So this is our initial quadratic. This is without taking the modulus, right? So it would look something like that. And of course, this is going off my screen, but I hope the idea is quite clear, right? So this entire green thing that I've sort of drawn over is basically x squared plus 9x plus 8. Okay? So the point is, in fact, when I actually look at point 1 and this point 2 that I've actually marked here, both of those points are intersecting with the line 1 minus x, right? So these two solutions that I actually have here, one of them is for this point and the other one is actually for this point here, right? And because this point is actually sort of closer to the origin, than say that point there, then I know sort of which one is going to be 1 and which one's going to be 2. So in fact, what I can say is, let me say here, I would say x equals minus 5 minus root 17. This is sort of further away from the origin. And x equals minus 5 plus root 17. And this is indeed closer to the origin. So actually, with one sort of calculation, I've managed to figure out 2 points at the same time. And this shouldn't surprise you that actually we're going to do the same thing with these points here. So let me call that point there 3, and let me call this point here 4. With the next calculation, we're going to figure out 3 and 4 at the same time. But we actually need, if I mark this in a different color, we actually need sort of this branch of our modulus function, right? And what's that branch going to look like? Well, we know what it's going to look like because we've actually got it there, right? It's an unhappy quadratic because there's a minus in front, okay? So we know this is going to be minus x squared plus 9x plus 8, but of course the minus applies to the whole thing. So I'm just going to solve for 3 and 4. I'm going to solve minus x squared plus 9x plus 8 equals to actually 1 minus x, right? And given the time pressures, I'm just going to write down the sort of solution here, and perhaps you can go check it yourself. And so we end up with two solutions. And again, the minus 4 minus root 7 solution is actually 0.3, or the x value of 0.3. And actually minus 4 plus root 7 is actually 4.4. So let's figure out exactly how these are going to look. So we've got sort of that thing there and that thing there and this thing here and actually this thing here, and we want the f of x being bigger than the g of x, so we basically want to look at this region here, and we also want to look at sort of this region here, and then we want to look at finally this region here. Because the inequality is actually strict, we're not going to count these points in themselves, okay? So I can just write down the solution now. So the final solution is actually going to be, I'm going to have x being less than minus 5 minus root 17, or x actually being between, say, minus 4 minus root 7 and minus 4 plus root 7, or x actually being bigger than minus 5 plus root 17. Okay, so that's a slightly involved solution, But I hope you found this example valuable, and that's a good place to end the video. So thank you for watching. Please do let us know in the comment section what you would like for us to make more videos on. Do hit the like and subscribe buttons, and as always, we will see you in the next video.